So today I'm talking to Scott Edgington, who's the Deputy Project Scientist of the Cassini mission. Scott, thanks very much for speaking to me.
Hello, Ian.
Um, the Cassini spacecraft arrived at the Saturn system in 2004, so it's been 13 years. I suppose the first question I kind of wanted to ask was, what has the spacecraft actually been doing for 13 years?
Well, we've been exploring the Saturn system, just about every aspect of the Saturn system. We have four primary disciplines that we're interested in, and one of those is to study Titan. In fact, that was one of the original goals of the Cassini mission to go back to this moon Titan, which Voyager had shown to be an interesting but enigmatic place, covered with haze and such. So scientists wanted to go there and explore it in further detail. But there's that beautiful planet with its rings in the middle, and so there's atmospheric scientists looking at the atmosphere. There's ring scientists very interested in studying the rings, their age, what they're made of. And then there's all the scientists who study all the tiny little moons that orbit around Saturn and the bigger moons that orbit around Saturn. And I'm sure we'll get around to talking about a few of them here.
Yes, definitely. How has the picture of the Saturnian system changed since Cassini arrived?
Well, probably the most significant discovery of Cassini, really, is the thought that these tiny little moons could have liquid water oceans and the right chemical ingredients and energy for life, a potentially habitable world. And there's several moons that we've already uh, discovered that have these liquid water oceans underneath their icy shells, one of which is Enceladus and the other Titan. And there's a few more that may or may not have that liquid water ocean. It requires more study.
Hmm. Actually, yeah, coming on to the subsurface ocean now, if the ocean exists below an icy crust, I suppose the obvious question might be why does the whole ocean not freeze?
Ah, yes. Well, these moons are tugged and pulled by Saturn itself and each other, and so you have these gravitational tides within them, which heats them up. It's sort of like a stress ball. If you squeeze it often enough, you're going to heat it up, and that heat is hot enough to melt water ice.
Hmm. And the presence of that heat and water, I believe, is what's kind of led people to conclude that Enceladus could potentially host life. Is this a possibility in your eyes?
Well, there's several lines of evidence pointing that there's the additional uh, nutrients necessary for life. For example, as we fly by this moon Enceladus, we've detected silica. Silica, tiny little grains of sand coming out in the geysers, which are mostly made of water ice, but there's salts, there's these silica grains. There's also a lot of methane, more methane than could be explained by simple chemical processes. There has to be some sort of active geology going on in order to generate all this methane. And the fact that you have these ingredients and they have been measured, and this tiny little moon is just giving samples to us as we fly through the plumes of this tiny little moon, it bolsters the idea that this might be a habitable place.
Hmm. And in terms of life, I mean, we're not talking about fish or anything like that, are we? We're talking about bacteria and things like that.
Yeah, tiny little things. Scientists look for the most obvious, simple ingredients and signs for life, things like amino acids or chemical signatures that might signify that something's going on there beyond the geology that we expect.
Hmm. You mentioned the plumes there that kind of spurt up from below the surface of Enceladus. and the fact that the Cassini spacecraft was able to fly through the plumes. I mean, how can you actually get a spacecraft to do that and know when the plume is going to spurt up and time it and get it to fly through, how you want it?
Well, as far as we could tell, the plumes are continuously giving, this material comes from the moon, the south pole of this moon, and so it's pretty much a continuous process in our lifetime since we've been there. So there's no sign of it letting up. Now, when we first flew by Enceladus, our magnetometer flew through the plume and or a part of the plume actually, and they detected the magnetic signature, and they said to the project, "Hey, something's up here. It's not what we would expect if this moon had a solid core." And so that got the navigators thinking. The scientists, of course, were eager to explore, a lot closer than we were, and we literally changed the trajectory to get closer to this moon. And eventually, after our prime mission, we had an extended mission approved, and that's where we really added a lot of opportunities to fly closer to the moon and explore it in greater detail.
So, is there actually much? It sounds like there is actually quite a lot of maneuverability with regards to the mission itself. So it's not this kind of rigid timetabled thing. If you discover something, you can kind of change. You can change the mission and where the spacecraft is going to go.
We had that possibility when we had a lot of fuel. Yes. Right now we're running out of fuel, which is the main reason why we have to dispose of the spacecraft. Once you run out of that fuel, you really have no control over the spacecraft. And so one of the NASA rules that we have to follow is that we cannot contaminate bodies that may or may not have the potential for life. And one of those bodies, of course, is Enceladus and Titan. And so you want to avoid hitting those objects at some point in the future. And so the safest thing to do is just dump it right into Saturn's atmosphere.
how how does the because the spacecraft is going to end its mission by basically smashing into Saturn, but does that not cause any problems with regards to NASA's kind of ethics, in that respect?
Oh no, the Saturnians don't care about this. No Saturnian is going to be harmed in the at the end of the mission.
Yes, well, I suppose that does bring us on nicely to Saturn. What do you think have been the biggest discoveries regarding Saturn? Because I suppose the two things that really capture the public's imagination are the rings and the its hexagon.
Hmm. Yes. Well, let's start with the rings. So we've been studying the rings ever since we've gotten there. We had some of the closest images were upon orbit insertion of the spacecraft. So literally day one, we're observing the rings up close and personal. Since then, we've looked at the rings in a lot of detail over time as the sun angle is changing on those on the rings. We've had opportunities to look at stars as they go behind the rings to determine how much mass is there and what the properties of these ring particles are. And we've shown that the rings are a very dynamic and interesting place where you have ring particles colliding with each other, forming clumps of material, some of which are smallish. We call these some of them propellers. You can't quite resolve the propellers, the core object, but you could see their effect. They generate waves. And then some of these propellers get big enough to become moons in their own right, and those generate waves, which further perturb the rings. The rings are extremely flat. You're talking tens of meters, maybe 30 meters high, except for the edges of the rings where the moons cause all this interaction to occur. And there you could get structures that tower, say, 1 kilometer in height. which we discovered in 2009 during the equinox phase of the mission. We see these moons having their effects. Some of the moons could be growing, one of which is at the edge of the A ring, a tiny little moon called Peggy, and an astronomer at London College, I believe, UCF. Is that right?
Imperial College?
Imperial College, London, yes.
Queen Mary.
Queen Mary? And
No,
Queen Mary, okay. Carl Murray is his name. He discovered this object at the edge of the A ring, and we've been observing this object for several years now, tracking it, seeing how it evolves. And there's a good question as to whether this object is going to become a moon in its own right and be basically ejected from the ring system to be an object on its own. And this object he calls Peggy, which was named after his mother-in-law, because he discovered it on her birthday.
Oh, that's nice. There was an incredible image I saw that was captured by Cassini of a small moon. I can't remember the name of the moon, but it was actually orbiting Saturn in the small gap, which I believe is called the Keeler Gap.
That would be Daphnis.
Did we know that like, we obviously didn't have that intricate a picture of Saturn before Cassini, but could we ever have imagined that small moons could be orbiting within that gap and indeed kind of creating gaps in the rings?
Well, it's amazing how textbook the rings have been in terms of the wave structures that we see. I was amazed when you see the image, and then you could go and identify the waves that are being generated and say that this wave is being caused by some moon out there, say Mimas, or in this case Daphnis. Daphnis is generating its own waves. So it's amazing how predictable it actually is. But you want to go and confirm your theories of the ring particle interactions, and that's what we're doing right now. And there are analogs with formations of solar systems, for example, where you do have ring systems and the planets form ring gaps in the rings and perturb their disks similarly to those at Saturn. So the rings of Saturn have been enlightening in the sense that it's been confirming what we do know, and it's been surprising us at times too. Just seeing the formation of some of these bodies like Peggy and seeing how they evolve and change over time, and is educational.
Yeah, you kind of touched upon a point there, and it reminded me of something that I read. I can't remember who said this, but there was an NASA scientist who said that the Saturn system is almost like its own mini solar system, and that we could actually learn a lot about the formation of our own solar system through studying Saturn and how its moons interact with one another. Is that the case?
Yeah, how they interact, how the ring system evolves over time. As you carve out these gaps, you have material moving around, some of which are drawn towards the moon and end up sticking to the moon, and hence the moon grows. And then you have these other effects. When you perturb something, it generates turbulence, and out of that turbulence could be born another moon, as far as we know. So there's similarities to what we think solar systems might be doing, the physics that govern those systems.
It's incredible. But we definitely have to touch upon the hexagon as well.
Yes.
Have we been able to kind of definitively say what it is and why it's hexagon shaped?
Yes. The hexagon is an example of what we call a jet stream here on Earth. If you imagine the jet stream on Earth, it's an organized pattern of winds that blow around the Earth, and you have air that travels over mountains, up the slopes of mountains, down the slopes of mountains, which affect the shape of this of the jet streams here on Earth. On Saturn, we're seeing this jet stream in its purest form because you don't have land to perturb the jet stream, and you also don't have hot oceans, cold oceans that also would perturb the jet stream. So that allows for a situation where you could generate a wave of air traveling around the planet. And it just so happens that this wave is six-sided. It could be five-sided, it could be seven. Why it's six, we don't know at this time, but it tells us something about how the atmosphere is structured in that region of Saturn. We've looked for a similar wave at Jupiter, but we haven't seen it. But there's a long time to explore with the Juno mission. And that mission is effectively just getting started as Cassini winds down its mission.
Yes.
But yeah, you're looking at a phenomena that is, just a pure result of the laws of fluid dynamics as we know them.
I assume there have been kind of attempts to recreate that through computer modeling in order to kind of work your way backwards.
And even laboratory work. I have colleagues at University of Oxford who have laboratory setups that generate waves like this, and they've been able to generate waves of five-sided waves, six-sided waves, seven-sided waves, and by studying this in the lab, that gives you some ground truth as to whether your computer models or your theories are correct.
So Cassini's due to end its mission in September, but between now and then, it's doing its kind of grand finale. And one of the phrases that we keep hearing is the ring grazing orbits. Can you explain it? Can you explain exactly what that means?
Yes. So back in November, we embarked on a series of orbits that basically pulled the Cassini spacecraft closer to the planet. And in the first phase, about 6 months, we have the periaps of the spacecraft, the closest point of the orbit, really close to the F ring. In fact, yesterday we got as close to the F ring as we will ever get in this mission, about 7,800 kilometers distance from the F ring. We've never been closer. The ring scientists are excited by this because, of course, they get up close views of the rings themselves, especially the outer edges. And so we've been doing this since November. I believe we just gone through 17 of 20 periaps passes through this region. And then in April, at the end of April, April 26th to be exact, we embark on this mission that will take the spacecraft in between the rings of Saturn and the atmosphere itself. It's a gap of about 2,000 to 3,000 kilometers, and our imaging scientists say that there's nothing there, and so we're trusting them, and we're going to go through this gap, and we're going to do that 22 times. These are new regions that have never been explored with the spacecraft, and now that we're out of fuel, we could take more risk and use the spacecraft to explore these other regions, which were not possible to explore earlier in the mission.
And then, obviously, as we've said, its final act will be to crash into Saturn, but presumably it will continue to collect and send back data just until it actually crashes. What sort of data or images can we expect to get in those final minutes?
Yes. The whole 22 orbits, actually, we're exploring Saturn in closer detail. We're detecting its gravity field. Throughout the mission, we've been outside of the rings, and so we've been measuring the gravity of the planet and the rings. And now that you're in between them, you could actually separate out the two and determine what is the gravity of Saturn itself and what is the gravity of the rings. And that will give us an idea of what the mass of the rings are. So that's one science objective. And then there's been this mystery as to why the magnetic field itself is not tilted. And the question is, maybe being outside of the rings, somehow that masks what the inner magnetic field is like. And so being up close and personal, we'll be able to detect that magnetic field up close and personal. And that will tell us something about, one, whether there is a tilt to Saturn's magnetic field, well, it will also tell us something about the interior, where the plasma inside the interior of Saturn exists. So those are two of our top science goals, in addition to flying through there, detecting whatever ring particles might be there, looking at the atmosphere itself, literally sniffing the atmosphere, because we're going to be traveling through the upper reaches of the atmosphere. And so those are some of our top science goals. In addition, we're going to get these, really high resolution images of Saturn closer than ever before. We're even going to bounce a radar signal off the clouds of Saturn and see what we see. So some exciting stuff there. And then during the final plunge, we're going to collect data all the way down until we lose the signal of the spacecraft. And so there we'll be literally sniffing the atmosphere, detecting its composition and temperature structure.
Absolutely incredible.
Hmm.
Most of our readers will remember towards the end of the Rosetta mission to study Comet 67P. Right up until the very end, we got really, really close-up shots of the comet. Can we expect something as exciting as that from the end of the Cassini mission?
Yeah, we have our final farewell images. They're already in the planning stages, and so you could expect images from that phase. At some point, I believe 4 hours out, we point the spacecraft such that our mass spectrometer, though, could detect the atmosphere of Saturn, because we want to see what's there. And so we'll be doing that, and I believe there's a final image about 4 hours out as we go embark on the last few hours of Cassini.
Fantastic. Well,
Mm.
thanks very much for speaking to me, Scott. I just wanted to wish you and the whole Cassini team the best of luck. I'm really, really looking forward to seeing the final pieces of data as they come in.
Oh, so are we. We're going to be here at 3 a.m. in the morning Pacific time, watching that signal as it sends down the final bits of data from Cassini, and it's going to be hopefully we'll get pretty deep before we lose that signal.
And presumably then there'll be time for a few beers afterwards.
Yes, and a big party.
Great. Well, we'll look forward to that. And again, Scott, thanks very much for speaking to me.
Well, thank you for having me.